and go ahead and share my screen. I remember one thing I didn't say there with that last example problem was that I still could ask to solve, say, reaction forces, what the bending stress is, maximum bending stress, what is the factor of safety, and remember, if you're given the problem, you still can draw your free body diagram to figure out what your reaction forces are. For this one, the maximum bending moment would occur in the center of the beam. So my route to that would just be draw a free body diagram of the left-hand side to the center of the beam, and then figure out what that internal moment is. When you're doing that, drawing your free body diagram to the center of the beam, again, you're just doing it just to the left, an infinitesimal amount of where that 8 kilonewton force is applied. And that will give you what the moment is at the center of the beam. For the length, you can still enter 1.5 meters, but that 8 kilonewton force shows up then in the reaction force, so it is being accounted for in that process. And then we get to statically indeterminate beams, and here we might need to pull up Shigley's tables. We'll see if we have enough from Hibbeler to be able to do this. But then for statically indeterminate beams, if you were to draw, say, your free body diagram and sum your forces and moments, you would still have more unknowns than the number of equations. So it's statically indeterminate. You really can't solve it based on your free body diagram alone. And so there, what you typically do is replace one of the boundary conditions with the corresponding reactions that would occur at that point, and then apply our principle of superposition as we did previously, and then define those compatibility constraints. If we're removing a fixed boundary here and replacing those with the corresponding vertical load and moment, we still have to satisfy that the displacement here at A is equal to 0 and that the slope at A is equal to 0. So those become then compatibility type constraints or boundary type constraints. And so that's our goal then, is for the following fixed beam and the distributed load only over half of the beam, what we want to do is find the reactions, the reaction forces at A and B. And that's really kind of the main complication with statically indeterminate. Once you know what the reaction forces are based on applying compatibility, then you could always go back through and figure out what the internal moment is as a function of X. You could figure out what the displacement is at the center of the beam. All that stuff you could determine once you know what the reaction forces are or their relationship with the loading in the geometry. So this is going to be another example problem with letters and not numbers. The compatibility constraints I mentioned again, the displacement at A has to be equal to 0 and the slope at A has to be equal to 0. And X is being defined from the left-hand side of the beam and Y vertically upward. And so looking at that, V, the displacement is going to be 0 based on that combination of the displacement at X equal to 0 due to the distributed load plus the displacement due to the load AY plus the displacement caused by that moment at A. And so this is, again, principle of superposition that we're using. We're just adding all those contributions of displacement together, but then we have to keep track of sign, an upward displacement being positive, a downward displacement being negative. And we're going to make use then of our tables to figure all this out. So we want a distributed load over half of the beam for a fixed free type situation, cantilevered. This is half the beam, but it's a pin, so that doesn't work. Keep going down. This is over the full length of the beam. That doesn't work. And we finally find one on that last slide where we have a fixed free beam, cantilevered beam with a distributed load over half of that. And then we have to look at the orientation that this would cause. The main thing is this is going to be deflecting downward, and so that would be a negative displacement. And Vmax is a minus 7 WL to the fourth over 384 EI. And that maximum would occur at that far left side of the beam. So we can use that one directly. We'll come back to these when we look at the slope, but let's focus on displacement first to develop our third equation here. And then the next thing is a point load. We don't need to look that one up because we remembered that from Monday. The displacement due to a point load is, remember, PL cubed over 3EI. And so in this case, AY is going upward, which means it's going to have a positive deflection upward. And so our P in this case is AY times L cubed over 3EI. So we didn't need to look that one up because we remembered it from Monday. I don't remember what the slope of the beam is, so we'll have to go there when we're doing the next step. And then the moment we'll find on slide 4. And the same thing, our maximum displacement, this is going to cause the beam to deflect upward. And so that's going to be equal to MA times L squared over 2EI based on what's provided in the table there. And so this was really nice that we could make use of that Vmax term in all 3 of those loading scenarios. And so that defines then our superposition combination of all loadings. And really what we're trying to do is to solve for AY, MA, BY, MB, all as a function of, say, the W distributed load and the length and the E and the I. And so this is getting us to that point. And so right now we have one equation and 2 unknowns, AY and MA. And so now let's look at the slope. The slope constraint was that has to also be 0 at A. And so we can look at all 3 of those parameters. First one, looking at the slope, I'm going to slide this back up just a little bit. The W is going to cause this to bend down in this manner. So that slope is going to be upward to the right, which is a positive slope. And so that's what you have to be careful for here. When you look it up in the table, sorry, we're on the top one there, it shows up as a minus WL cubed over 4080 EI, but that's just based on how the beam is supported and it's sloping downward to the right, which was a negative. So the magnitude is correct, but the sign needs to be positive based on how this is orientated. So that's probably the thing that you have to look out for the most, is making sure your sign is correct as you're pulling these off from the table. And so we'll put that in as a positive WL cubed over 48 EI. And then A of Y, that's going to cause that to push up and then come back down. So that's going to be a negative, as well as the MA. Both of those will be negative values. I will go back here to the third one, because I don't remember the slope. the maximum slope. And so there again, the slope here is a minus PL squared over 2EI because it's sloping downward to the right. When this deflects upward, it'll do the same. It's sloping downward to the right. So minus PL squared over 2EI. P in this case is AY. So I have minus AY L squared over 2EI, pulling that directly from the table. And then the moment, again, this situation, the moment is causing that to slope up to the right. In our situation, it's going to cause it to bend up, and it's going to be coming down, so it's going to be a negative. And so here it shows up as positive, but we have to enter it in as negative based on our conditions that we're seeing. And so we end up with a minus MAL over EI is equal to 0. And so we now have then 2 equations and 2 unknowns. AY and MA are unknowns with respect to WL and EI. And so that's our goal of solving the reaction forces, is getting those in relation to the loading and the geometry, so that we can uniquely define those based on those parameters. When we do that, we'll have the boundary conditions on the left-hand side, or those reactions. And so then we could sum moments for the entirety of the beam and solve for MB. And we can sum forces in the Y and solve for PY. But if we were to do that step now, we would have 2 equations and 4 unknowns. So it would be statically indeterminate. So this process allows us to solve for AY and MA. And we just need to solve the 2 equations, 2 unknowns. And I just did that with the Gauss elimination type method. I kind of saw that let's see, this last term in each one of them, if I were to multiply everything through here by an L over 2, I would end up with a minus MAL squared over 2EI. And then if I sum those together, those 2 terms would then cancel out. And so all I'm going to do then from a Gauss elimination standpoint is take equation 3 plus L over 2 times equation 4. And life will be easy to solve for these. And so looking at that, we're really adding the left-hand side of the equations, which are 0 plus 0 gives us still 0 for the displacement and slope. And then when we add the right-hand side of the equations, we're doing equation 3 directly, so minus 7 WL to the 4th over 384 EI plus an AYL cubed over 3 EI plus an MAL squared over 2 EI. And then now adding in the second equation times L over 2, we'll end up with plus a WL to the 4th over 96 EI minus an AYL cubed over 4 EI minus an MAL squared over 2 EI. And so Gauss elimination is nice. Those are getting canceled out now in that process. And we have 1 equation, 1 unknown to solve then for A of Y. And I believe I moved A of Y to the left-hand side. So that was a positive AYL cubed over 4 EI minus the AYL cubed over 3 EI. This is going to be equal to, then I put the positive one first, WL to the 4th over 96 EI minus the 7 WL to the 4th over 384 EI. And from that standpoint, then I found common denominators on the left and the right side. And so 12 is a common denominator on the left-hand side. And so we end up with 3 minus 4 will give us a minus AYL cubed over 12EI. 384 is a common denominator on the right-hand side. So that'll give us 4 over 384 minus 7 will give us a minus 3 WL to the fourth over 384 EI. And we can solve out AY. We have two negative signs, so they will cancel one another out. And then we'll have 3 WL to the fourth over 384 EI, and then times 12 EI over L cubed. And so we'll have the EIs will cancel. 384 goes into 12 32 times. And we have an L to the fourth canceling with an L cubed. So we end up with AY is equal to 3 WL over 32. And then after that, I went ahead and solved for what BY was, just summing forces in the Y. You'd have a BY plus AY minus a WL over 2 is equal to 0. And so BY is just equal to WL over 2 minus the 3 WL over 32. And so 32 is a common denominator, and we end up with BY then being 13 WL over 32. If we put equation 5 into equation 4, we can solve for M of A then. And so again, just more algebra. We plugged the L squared, let's see. We substituted in the 3 WL over 32, and for that, back into equation 4. And so just simplifying down again, you'll find that the moment at A is equal to a minus 5 WL squared over 192. And then summing moments about B, the right-hand side, you'd have a MB minus an MA plus the WL over 2 times L over 4 minus the AYL. And kind of looking at where these terms are coming from, the force coming from this distributed load would be equal to a W times L over 2. And then the distance that it would act from B would be L over 4 in the center. And so we end up with the WL over 2 representing the concentrated force, and the L over 4 representing the moment arm associated with that. And then summing moments about this, we'd have a AY times an L in a clockwise direction. And so again, we're just making use of that free body diagram there on the top. We know what M of A is, and we know what A of Y is. And so we can make those substitutions and solve for M of B as minus 11 WL squared over 192. And so that's the hardest part of the problem there, is determining what those reactions are, those vertical forces AY and BY, and then those moments. Once you've solved this for a statically indeterminate problem, then it's just a matter of continuing on as you would before. If you wanted to figure out what the moment was, then as a function of X, you could just draw a free body diagram for the section and then continue on. You'd have to draw another free body diagram and then you'd have to apply continuity between the two to develop the elastic curve. But I think generally for these superposition problems, that's the main goal, is figuring out the reaction forces. We'll just kind of assume that you could do the next step if you really wanted to, in terms of figuring out those elastic curves in relation to that. The other thing is you could make use of the tables and just sum those elastic curves together based on what was provided. And there you would still have to keep track of the sign out in the front for this loading condition. Is it going to be a negative displacement or positive? But that would enable you to solve for that as well for your elastic curves. Let's see. Are there any questions over that one at all?
No, that made sense.
All right. And so that's really all there is to it. On Monday, we were really able to go through and do things by hand, the derivations, taking your integration, solving for those. We had one example where we did that today with applying continuity as well. But then we're able to see the flip side of doing that same problem using the tables, and then continuing on with using tables where the principle of superposition comes in handy, and solving problems much quicker with making use of those tables. But I guess I'll need to get the next homework posted to D2L. So do take a look at that. I'll get that posted here soon, here before the end of the day. And that'll be due for not this Saturday, but next Saturday over these chapter 12 problems. And I think that'll do it for today. And then again, Friday will just be a help session. So I'll show up and then answer any questions that have come up by email during that time frame, or answer any questions that anyone brings forward during that live session. So might be a short class period on Friday, but I think we'll call that good for today, and we'll see you on Friday.
Yep, see you on Friday.
Yep, thanks.
Thank you. Have a good day.
You too.